is the fifth, right? I just want to refresh your memory on the graphs that we looked at last time. Okay. So this in the case of a between 0 and 1. And this in the other possibility in which a is greater than 1. We have to summarize these two and commit them to memory. So the exponential function with the base less than 1, as I mentioned, looks like this. And of course, it crosses at 1, 0, comma 1, of course. And as an example is 1/2 to the x power. If I want to graph the inverse function on the same coordinate system, remember I have to graph this line, which is y equals x, because where the function is crossing, so will y equals x, so will the inverse function. So it's also decreasing. So this is function log base 1/2 of x. For an exponential and log to be inverses of each other, they must have the same base. Okay, the other situation, it's in a way nicer, I would say. So this is 2 to the x, and again, if I want to graph both on the same coordinate system, I have to draw y equals x. And of course, this is 1, and this is 1, and this is 1. So this will be log base 2 of x. Any questions? Yes. Please let me know what it's not clear?
No, I was asking that there was.
This?
No. Yeah, in front of them.
It's the base. The base of the exponential and log is called a. It's between 0 and 1. There are two options. One for the base to be between 0 and 1, and the other one to be greater than 1. Is that okay?
Mm-hmm.
So basically, this is what we discussed last time. We also said that log base b of x is y, this is a log equation, is equivalent to the base raised to this number is this number. So b raised to y equals x. So this was that very important concept that says, and we're going to use it in the entire chapter many, many times. A log equation can be replaced by an exponential one, and vice versa. Having this in mind, let's try to determine the domain of another log function and also graph it using transformations. Any questions for me? Is this okay? Okay, so let's say 76, f of x equals x, I'm sorry, log base 5 of x plus 6. We're asked to find to do two things. Number one, domain.
What is
And
that for the a?
Yeah.
The less than sign?
It's a 0. It's a 0.
you mean this one?
Yeah.
So a is a number between 0 and 1, or a is a number greater than 1. If it is between 0 and 1, these are the graphs. If it's between 1 and infinity, these are the graphs for the exponential and log. Is it better? Questions? Is this okay? Stop me anytime, please.
Is that a B?
Yes, I put B here. So this is B. Put any base. As long as you are consistent, if you put A here, you have to put A here. Any base you want. Good. So then we are asked to graph. Okay. So what do I have to write in order to determine the domain of this function? Remember, when we find a domain, we don't destroy anything. We just don't, we have to write something and solve. So what do I write? How do I solve this? Oops. I said x plus 6 not equal to 0. 0 is not allowed. It's a vertical asymptote. Careful. It's similar to the square root function, except 0. So what do I have to write? Let's go back to the last problem from last time. if you have it. And just mimic that and tell me what you have to write. Say it again. Exactly, greater than. B. So I have to write that x plus 6 is greater than 0. X plus 6 greater than 0. This will give us the domain. So x greater than negative 6. So the domain of this function is negative 6 to infinity. Very good. Yes? Let's look at the two graphs of the log function. As you see, it's not, nothing appears on the left-hand side. This is the graph of the log. It starts at 0. But this is the pure log function. One second, Steve. So as long as I have x, it has to be the domain between 0 and infinity. But I don't have x. This is a transformation. So what is a transformation doing? What does log base 5 of x plus 5 do to this one? To the, that's why I said, please, I'm begging you to redo all problems from each test every weekend. Because then you're going to have to start from scratch and review everything. And that will be a lot of time, a lot of energy and stress. So where does this go when we change x into x plus 6? Left 6. That's why the domain is from negative 6 to infinity. Yes, Stephen?
Will there ever be a chance that we'll have to set it less than 0?
Log is not applied to numbers less than 0. Look at the function. It's defined from 0 to infinity. Here's log in green from 0 to infinity. It's defined on the range of the exponential. So let's write that. Maybe that will trigger your memory. That's fine. So the exponential is defined on all real numbers and has the range 0 to infinity. Look at the graphs. Look at the graph of the exponential from 0 to infinity. Look at the graph of the exponential from 0 to infinity. So what is the domain of the log and the range of the log? Knowing that its log is the inverse of the exponential. Log is the inverse function of the exponential. What will be the domain of the log? Of course. And the range? Right. It's the inverse of what the exponential does. So that's the reason why log is defined on 0 to infinity. It's the inverse of the exponential. And the range of the exponential is 0 to infinity. That's why the domain of log is 0 to infinity. Does that make sense? Okay, very good. So we determined the domain. So now we want to graph this function. You already told me what to do, but let's write it again. So what is the base function? So our function is f of x equals log base 5 of x plus 6. So what is the base function here? Say it again. Five is not a, say it again. Of course. Log base 5 of x. The function cannot have just 5, right? Cannot be negative 5. We're talking about the log function. And
What
it's
was the question?
what is the base function? The base function is log base 5 of x. So then the only transformation on this to determine or get this function would be log base 5 of x plus 6. And what transformation is this? When we change x into x plus 6. Very good. That's all I need you to repeat. Very good. Awesome. So now, what is the vertical asymptote of the log function? Let's look at the graph. Let's look at the log with base less than 1 and the log with base greater than 1. What is the vertical asymptote of this graph? X equals? Right, correct. No, the original one. Abby's always ahead of me, always. Thank you. So the original one, this or this, has the vertical asymptote, what? 0. So now when I shift the graph 6 units to your left, what happens to the vertical asymptote? Right. I have to move it first. Yes. So that's what I want you to remember. First, I have to shift the asymptote. 1, 2, 3, 4, 5, 6. So let's graph first the function. I should have done that first. I'm sorry, I jumped. So this is log base 5 of x. And indeed, crossing always, it's a pure exponential function. It will cross where? X. Yes. Awesome. So now this is my indicator. This is the point that I use to graph the function or show where it's going. So where will this point go? And I'll put it there and graph the function. So from 1, we'll move to, very good, right here. So this is the new graph, which is log base 5 of x plus 6. And we knew that because the domain is -6 to infinity. Is that okay, everyone? Is that clear? Yes? Okay. Do you think we need more examples with graphing log functions?
Yes, please.
Very good. Perfect. Any preference, or can I make one up?
Yes, choice.
Okay. So let's say 73. 73 has g of x equals 2 minus natural log x. First, I notice that this function is not presented in the correct order, so I will rearrange it. How?
What does that say?
2 minus ln x. So how will I rewrite it? Obviously, negative ln x plus 2. Yeah, so the quantity with the variable is always first, and then the free term is always last. Because it's easier to identify the transformations, not because it's required at this moment in time. Okay, can anyone give us the base function? Of course, ln x. The first transformation on ln x, or natural log x. Which transformation? Say it again. No, because that doesn't touch x. I don't have parentheses. If I had parentheses, I would have said yes, but there are no parentheses. Yes, because that's the first ln x, that's the first operation in order of operations. Yes. What does this do? Yes, reflect with respect to? Awesome. Reflect with respect to the x-axis. Very good. Number 2 is a transformation on number 1. So this will be natural log, negative natural log plus 2. What does this do to graph from number 1? Awesome. Do we all agree with up to? Yes? Yes? Okay, so now I have to remember how to graph natural log. I have to graph the base function first. Do I graph it increasing or decreasing? So let's go back. We have 2 options. We have this option for natural log, and we have this option for natural log. Which one? Yes, because base e is greater than 1. Awesome. So this is natural log x, and it crosses where?
1.
Yes, because it's the base function. Good. Then you told me to flip it. No problem. I will. So this is negative natural log x. Yes, with respect to the x-axis. We multiply all y values by -1. So when I multiply this by -1, it becomes positive. When I multiply this height by -1, it becomes negative. Perfect. So now I would like to know where does this graph, the green graph, move? It moves up to. So now please give me the indicator. Where will I move the indicator? Yes, awesome. So here it is, and here's the graph. Negative natural log x plus 2. Very good. Can anyone give us a domain of this function? Let's look at the graph. The graph will tell us without doing anything. Say it again.
2 to infinity. Oh, 1. Still 1. The domain for asymptote? Oh, 0 to infinity.
Awesome. Domain 0 to infinity. It's natural log x. X must be greater than 0. Very good. So please keep that in mind. Now I would like to look at a word problem. So you can see, and I'll ask you, I'll give you a few options and you choose. One option is to look at a function that models the wife's weekly housework hours. It's a natural log function. Then models another function that models the husband's weekly housework hours. Then we can look at students in a psychology class taking a final exam. Which one? Okay, the psychology exam then. If you don't want to choose, I will.
What number is it?
That's number 119 on page 491. So let's read the problem. Students in a psychology class took a final examination. As part of an experiment to see how much of the course content they remembered over time, they took equivalent forms of the exam in monthly intervals thereafter. So they took the final exam today, and then they took another exam a month later, and another one a month later, and so on and so forth. And the average score for the group, so f of x or f of t in this case, that's the average score. Okay, this is not a good color. Sorry about that. Is 88 minus 15 natural log t plus 1 for t between 0 months and 12 months. F of t equals 88 minus 15 natural log of t plus 1. What was the average score on the original exam? Part A. What was the average score on the original exam?
88 minus 15.
So what do I have to find? So I'm given a function that represents the average. Say it again. So I'm given a function and I'm asked to find what happened originally. When we talk about what happened originally, what do we really mean?
The base function. Base function.
Yeah, the base function is natural log t. We're not trying to use transformations on this, but you're right. The base function is natural log t. If you want, shift it to the left 1, multiplied by 15 vertical stretch, flipped, and then up 88. So if we want to decompose it like that, we can. But the question is asking us, what was the average score on the original exam? By original exam, what do we really mean? Yes, when time is, exactly, that's all I want you to say. So by original, we mean initial. Yes. So we want to find f of 0. 0 months. So t is in months from 0 to 12. So I have 88 minus 15 natural log of 0 plus 1. We're going to put it in the graphing calculator. However, let's determine this now, just this piece. How much is 0 plus 1? Correct. So let's determine natural log of 1. Let's say we don't know what it is, but we know that we can change this into an exponential equation. I don't see a base here, but I know what it is. What is the base of the natural log? Indeed, e. E raised to some power is 1. So remember, this is one of the most important concepts. I would consider the most important. E raised to what power is 1? E raised to what power is 1? Say it again. Yes, natural log means base e. So here's how you also remember it. That's another way of remembering it. See, natural log ln, and you see the base e here, e to the x.
Yeah, but in that first equation, what did that go? Is that say log b or log e in the box?
Here,
That's a b or an e?
b raised to y equals x. So which number I raise e to get 1? Correct. So this is 0. So then this will be 0. How much is 0 times 15? How much is 88 minus 0? 88. So the score, the question was, the score, what was the average score on the original exam? It's 88. Part B, what was the average score after 2 months? T equals 2 months, and then T equals 4, and so on and so forth. So I'm going to create a table, f of t, and I'm going to put 0, 2, they want 2, they want 4, they want 6, then want 8, they want 10, and 1 year. So let's go to the graphing calculator, and let's plug it in. So in y equals, clear if you have whatever in there. So we had 88 minus 15, natural log, in parentheses, x plus 1. Then I will create the table, second table, and put all those numbers in there. I already have the answer for 0, but let's put it again. 2, 4, 6, 8, 10, and 12. So originally, the average score was 88, and then 2 months later, it dropped to 72% roughly. 4 months later, it dropped to 64%, and then 59, and then 55, and then 52, and then 49, roughly 50. So I'm going to put these numbers in the table. So this is 88, and then 72, and then 64 roughly, and then 59, and then 55, and then 52, and then roughly I would say 50. So in a year, roughly, if we don't review what we study, what we're interested in a year, our knowledge of the topic drops from 100% or from 88 to 50%. Okay. Part C, sketch the graph of either by hand or with the graphing calculator. Describe what the graph indicates in terms we already know what it describes. So let's take a look at the graph. Since we are only looking between what x? Zero to 12. So I'm going to put 0 to 12 for x. Knowledge cannot be negative, so but I want to see the x-axis, so I'm going to write -2. But I know that the maximum, the original value for y was 88. So I'm going to go over, let's say, 100 with a scale of 20 and just press enter. So here's the graph coming from 88. Oh, sorry. So coming from 88, so let me go back, sorry about that. So we had the function in there, and then I changed the viewing window, 0 to 12 with a scale of 2, and y minimum -2 to y maximum of 100 with a scale of 20. And as expected, because we already had the y values, it's coming from 88 and it decreases to roughly 50% a year later. So this is 50, or score, average score of 50 from an average score of 88. So this is an example of a logarithmic function. It has natural log in it. 88 minus 15, natural log of t plus 1. Okay, any questions for me? Any questions? Any questions? Okay, so let's continue with 4.3. Properties. Properties of log. Yes, any questions? Jesse, go ahead.
Yeah, I was talking.
If there is anything I could do to help, you'll always stop me if there is anything. This is the material. What I did not create the curriculum. I just have to follow it. Okay, so properties of logs. This function log has 3 properties that no other function has. Okay, so let's study these properties and then work with those. Here's one property: log of a multiplied by b in any base. Let's put a, any base you want. So log applied to a product is the sum of logs. Log base a of a, log base a of b. So this is what is called the product rule. Product rule. I want you to understand this rule going backwards and forward. Meaning, if I'm given log of a product, I will change it into sum of logs. If I'm given sum of logs in the same base, I can change it back into log applied to a product. So let's look at an example here so we get the feel of it. So if I have log of 2x, I don't see a base here. What kind of log is this? Base 10. It's common log. So this will become log of 2 plus log of x. Correct.
Is that 2 plus
2x. So this is log 2x, common log applied to 2x, equals log of 2 plus log of x. Now I can go backwards. So log of 2 plus log of x is nothing else but log of twice x. So let's also look at an example going backwards. So let's say I have natural log of 3 plus natural log of y. Where does this come from? Or what can I change it into? Natural log? Exactly. So this is a property that no other function has. It's called the product rule. Awesome. Now let's look at the next one. Log base a of a over b. A wild guess. What do you think this will equal to? If the product was a sum, the ratio, what do you think the ratio would equal to? A difference. Correct. Very good. Log base a of a minus log base a of b. So here's an example. Log of x over y. What does this equal to? Perfect. And I can go backwards. Log of x minus log of y. If log has positive in front, its quantity comes from the top. If it has negative in front, its quantity comes from the denominator of this expression. And of course, this is called the quotient rule. And there is one more, the last property that no other function has is this. Log in any base, let's say base a, of a raised to power x. This power becomes a factor in front. Factor meaning multiplies log. So x log base a of a. Multiplication. It becomes a factor. Of course, this is called the power rule. Power rule. And here's an example. Log base 5 of x cubed. What do you think this will equal to?
3 logs.
3 log base 5 of x. Now, if I see a number in front of log that is a factor, multiplies log, here's an example. Let's say negative 2 log x. I can go back and write log x to which power?
1/2? No,
Exactly what I see. I just have to copy it. And you can rewrite it as log of, instead of x to negative 2, we can write x to negative 2 is a fraction. It's just another way of writing 1 over 1 over, indeed, 1 over x squared. Good. So now let's practice these. Before we practice, I would like to talk about one more piece of information, if you want, the change of base formula. The sophisticated calculators, which I don't have one of, may allow you to put any base. I don't think my calculator does that. But we do have two bases. What base is this? ln?
Natural log.
E, base E. What base is this? log? 10. So these are the ones that we have in the graphing calculator. And let's suppose we want to approximate log base 3 of 7. And let's suppose our calculators do not allow us to put the base 3. How do I do that? So there is what is called the change of base formula. I can still calculate it, but I will have to use the change of base formula, which is log base 3 of 7 is, it doesn't matter which log you apply or which log you use, but you have to be consistent. If you use base 10, it's log applied to the number over log applied to the previous base. Notice one thing, that this is not this. This is not log of x over log of y. This is log applied to a ratio. This is something else. This is log of 7, everything over log of 3. Can anyone mimic the same thing but with natural log this time? Very good. Over. That's it. The number has to be the same. It doesn't matter. Let's put in the graphing calculator and see what happens. So go back to graphing calculator. So let's say log 7 divided by log 3 must be the same with natural log 7 divided by natural log 3. As long as you are consistent, there is only one number. And let's say I have doubts about my work. I want to check this. How do I check? So let's go back here for a second. Let's say that the approximation was 1.7712. I want to check. So we are told that log base 3 of 7 equals 1.7712. How do I check this? 3, the very, 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 very important concept from before. 3 raised to will equal. Okay, let's try. But I want to use the entire number. I don't want to use the approximation. So 3 caret the previous answer. And when I hit enter, what should I get? If my answer is correct, exactly 7, indeed. If I don't get 7, something is wrong. My answer is incorrect. Any questions on this? Okay, now let's.
How do you do the previous thing?
Oh yeah, yes, sure. So 3 to the previous caret.
Can't see it.
Oh, it didn't change? Sorry. So 3 caret previous answer. I'm not going to get the same answer because now if the previous answer is 7,
Yeah.
so it's going to give me something totally different.
Right. Gotcha.
So 3 caret previous answer. And press enter. Why I do that? Because I want the calculator to include everything. If I use 4 digits or 6 digits or 10 digits will give me an approximation. It will not give me the exact. Very good. Awesome. So now on page 501, we have tons of examples of how to use these properties, these 3 properties. Condensing and expanding. So let's start with expanding. Expanding log expressions. Okay, so let's start with the easy one, like let's say 27. In 27, we have log base b of x squared y divided by z squared. Okay, listen, this looks complicated. It's not at all. You'll see in a moment. We are asked to expand it and rewrite it with simple logs. So from a complicated expression, log of a complicated expression, we want to present it with simple logs. So the first step would be to look at the ratio. Can anyone tell us how to change log applied to a ratio?
Log B,
Log base b of,
of the numerator.
very good, x squared y, with parentheses or not is okay, and then
Minus.
perfect. Log base b of z squared. Awesome. So first we apply the quotient. So log of the top over the bottom is log of the top minus log of the bottom. And now we have log applied to a product. So I continue. The quotient is gone. So now I want to apply log to a product. So I get log of what?
First term.
Yes, of the first factor, x squared, yes. Log base b of x squared, yes.
Log base B to y.
What is the, yes, awesome. Log base b of y and minus log base b of z squared. So I'm done with products and ratios. First the ratio, then the product. But I do have one more property to apply. Which property is that? The power, yes. This will go in front as a factor. This will go in front as a factor, in front of its specific log. So this is 2 log base b of x plus log base b of y minus 2 log base b of z. I want to draw your, there is nothing else we can do. We applied all possible properties. There is nothing else. Now, I just want to draw your attention to something, because we're going to use this in the next few minutes. Which of these three quantities, I know it's a silly question, but bear with me. Which of these three quantities comes from the denominator? Z squared. Therefore, it's the only one with minus in front. Now, let's look at the other. How many of these come from the numerator? 2. The x and the y, correct? Notice that they both have positive in front. So keep that in mind. We're going to use that in a minute. But let's look at another example, like 36. Any questions on 27? Yes.
What page was that on?
27 on page 501. Thank you for reminding me. My apologies. Okay, so let's start 36. Same page. Log base 2 of the fifth root of x y to the fourth divided by 16. We're asked to do the same thing. We're asked to expand this to simple possible logs, apply all three properties or as many properties as we need to apply to simplify this completely into very, very simple logs. Say it again. So, can anyone tell us what is the fifth root? What power is the fifth root? No, the power 5 will be x. Yes, indeed. So this is the same with log base 2 of xy to the fourth over 16 raised to power 1/5. Awesome. That's our starting point.
Wait, what? Wait a second.
The fifth root is power 1/5.
So which way are we going? Are we going up there? Or are we going over here? Which one? What?
This was something else that I wanted to explain, but
Okay.
I already got the answer, so I stopped. Sorry about that. So the first property that we need to apply now is not the quotient, but exactly the power indeed. So let's apply the power rule first. So what do I have to write?
1/5 log.
Yes, 1/5 in front. Awesome. Very good. log base 2 of xy to the 4th divided by 16. Again, how many of these expressions that we are going to get to in a moment will have positive in front, and how many will have negative in front? 2 will have positive in front and only 1 negative, because there is only one quantity coming from the denominator, one factor. Very good, awesome. So then I keep 1/5 outside. So now please tell me what we have in brackets.
Log base 2 xy
Excellent.
minus
Yes.
log base 2
Of 16. Perfect. Now let's see if we can simplify this in any way, shape, or form. Let's work on this for a moment and then come back. So log base 2 of 16 is some number, but I know that I can change this into the most important concept in this chapter. Yes, 2 raised to question mark equals. Very good. So is there a number that I raise 2 to a power to get 16? Very good. Awesome. Well done. So now I can continue. 1/5. Now let's see what happens with log base 2 of xy to the 4th. Log base 2 of, very good, very good. Log base 2 of y to the 4th minus 4. Perfect. I have one more step to perform inside. Which step would be that? Yes, awesome. Log base 2 of x plus 4, log base 2 of y minus 4. The final step must be distributing 1/5, I'm sorry, to all terms. Can anyone dictate the first term?
1/5 y base 2x
Very good. Yes? 4/5 log base 2 of y minus. That's it. And this is it. So in order, yes, that's it. We cannot do anything else. This is expanding. We expanded the expression, the log applied to a complicated expression, into simple logs. Now the next step would be to go backwards, to condense. So, yes.
Hang on there.
Any questions for me? We're going to apply the same exact